Last time I showed you how to actually compute Maclaurin series expansions. And we came up with a few formulas. Here are some of the formulas that I'm just going to remind you of because we're going to use them. All right, so here's the expansion for e to the x, the hyperbolic cosine, the hyperbolic sine, and the sine. And we talked about last time how those things should make sense. I also would like to point out that they converge everywhere, right? Their interval of convergence is the real numbers minus infinity to infinity. Okay, additionally, we looked at the geometric series, and this is the geometric series where a is 1 and r is x. And we should know from our little formula at the very beginning of this chapter that 1 over 1 minus x is what? 1 plus x squared plus ... which we can write as the summation in running from 0 to infinity of x to the n. So those are all the common Maclaurin series, and now I'm going to show you how to get some uncommon ones. And we're going to do it by doing algebra and calculus on these series. The bottom line is this: Taylor expansions, and remember, a Maclaurin expansion is a special case of a Taylor expansion. Taylor expansions can be proven to be unique where they converge absolutely. What does that mean? That means if you have a Taylor expansion of a function, there's only one. And so I don't always have to go back to the definition of a Taylor expansion to be able to compute it. If I can take a known Taylor expansion and do a little calculus on it or a little algebra on it and come up with it, then I can come up with a Taylor expansion for other functions. Now let me show you what I mean by that. All right, so we're going to look at the first example. Suppose I want, and all I'm going to look at are Maclaurin expansions here. And for the exam, Maclaurin expansions are going to be what I concentrate on, what the book concentrates on. So they're going to be powers of x only, not x minus a. So suppose I wanted the Maclaurin expansion for the cosine of x squared. Well, I could use the definition of the Maclaurin expansion, but that's too hard. So how can I get this expansion some other way by doing a little algebra? Well, I can do it like this. I know what the expansion is for cosine x. And if you go up here and check cosine x, it's this. And now I'm going to go down there. And that's what I put here. So I know what the expansion of cosine x is. How do I get the expansion of cosine x squared? Well, the answer is common sense. It depends on how common your sense is. I just have to take this formula up here, and everywhere I see an x, I replace it with x squared. And life's that easy. And what I end up with is a Maclaurin expansion for the cosine of x squared. All right, so everywhere I see an x here, I replace it with x squared. I get the summation in running from 0 to infinity of x squared to the 2n times minus 1 to the n over 2n factorial. Now, for those of you who remember your rules of exponents, x squared to the 2n is x to the 2n times 2, which is x to the 4n. So this cleans up to be x to the 4n times minus 1 to the n over 2n factorial. And guess what? I have just computed the Maclaurin expansion for cosine x squared without using the definition. How do I know that it is the Maclaurin expansion? Because Taylor expansions are unique. All right. So if I can use an expansion I already know to get expansions I don't know just by doing a little algebra or even a little calculus. Let's look at example 2. Suppose I want the Maclaurin expansion for x squared sinh x. Well, I know what the expansion is for sinh x. And so if I want x squared sinh x, I just take x squared and multiply it by the expansion I already know. And then what can I do? Well, I can take the x squared inside. It becomes x squared times x to the 2n plus 1 over 2n plus 1 factorial. Again, if you know your rules of exponents, x squared times x to the 2n plus 1 is x to the 2n plus 1 plus 2, or x to the 2n plus 3. On the bottom, I still have 2n plus 1 factorial, and lo and behold, this is a Maclaurin expansion because it's in powers of x. Hence, it is the Maclaurin expansion for x squared sinh x. Get it? Life is that easy. All right, now let's do a few more. Suppose I want the Maclaurin expansion for 1 over 1 plus x. Well, I know the expansion for 1 over 1 minus x. That's my famous little geometric series. It is this. So if I want 1 over 1 plus x, I just have to figure out how to write it like this. Well, I could write it like that by 1 over 1 plus x is the same as 1 over 1 minus a minus x, right? Because minus a minus x is plus x. What does that do for me? Well, everywhere I see an x here, I replace it with a minus x. So I get minus x to the n, and by the way, minus x is minus 1 times x, all to the n. Rules of exponents again, that's minus 1 to the n times x to the n in running from 0 to infinity. Guess what? I just did the Maclaurin expansion for 1 over 1 plus x. Isn't that slick? All right, now compare this expansion, 1 over 1 plus x, to, at the very beginning, I have an expansion of 1 over 1 plus x, and guess what it is? It's exactly what I came up with. No surprise, math is true. All right, now let's look at the next example. Suppose I want the expansion for the arctangent of x. Well, I have to be a little smart. You should recall that the arctangent of x is the integral of 1 over 1 plus x squared dx. Yes? So that's what I'm going to use. But first, I have to get the expansion of 1 over 1 plus x squared. And then, you know what I'm going to do? I'm going to integrate it. Yes, I can do calculus on Maclaurin expansions, and it works. As long as the expansion is, in particular, absolutely convergent, which it will be in certain areas, all right? All right, so how do I get 1 over 1 plus x squared? Well, I know what 1 over 1 plus x is. Why? Because I just did it up here. So 1 over 1 plus x is summation in running from 0 to infinity of minus 1 to the n, x to the n. So how do I get 1 over 1 plus x squared? Well, the answer is everywhere I see an x here, I replace it with what? X squared. So I do that, minus 1 to the n times x squared to the n in running from 0 to infinity. And rules of exponents again, x squared all to the n is x to the 2n. And then if I want the arctangent, I just have to take this sum and integrate it. All right, so I do that. I integrate it. Well, I just integrate each piece. So all I really have to, minus 1 to the n goes along for the ride, it's a constant. I just have to integrate x to the 2n. What was my rule? X to the 2n plus 1 divided by 2n plus 1, yes? All right, there's my new series. But recall that anytime I do an indefinite integral, I have to add an arbitrary constant c. So I did that. So now the arctangent is this. The only thing I need to figure out is what c is. Well, how can I do that? Well, recall that the arctangent of 0 is an angle whose tangent is 0. And that angle has to fall between what? Minus pi halves and pi halves? Well, the angle that works is 0, yes? So if I take this equation and I plug in 0, here's what I get. 0 equals, and then everywhere I see an x here, I stick in 0, and then I have a plus c. Well, you should notice that every term here has an x in it, and when I plugged in 0, it went away. So what I get is 0 add c, which is nothing but c. Therefore, c is 0, which means what? The arctangent is just this piece, because c is 0. So I get the arctangent of x is the summation in running from 0 to infinity, minus 1 to the n, x to the 2n plus 1 over 2n plus 1. Now, let's see if that fits with what we have for it up here. Minus 1 to the n, x to the 2n over 2n plus 1. Ha! It does. So I get a warm, fuzzy feeling. I did it right. And that math is true.